Okay, folks, so we're going to do another experiment here. I have my two helpers. What are your names?
Caleb!
What's your name, honey?
Briar!
Briar. Caleb and Briar. Okay, so let's look in front of us. We have two bowls. This one has a number 1. This one has a number 2. Let's first look inside our bowls. What can you tell me? Just look at both of them. What can you tell me about what you see in there, Caleb? What kind of stuff do you see?
Salt!
Salt, maybe? Which one do you think is salt? Or both of them?
I think they're both salt.
Yeah, what color are they?
White.
And are they powdery or hard? You want to feel them?
They're squishy.
Squishy. What does it feel like to you, Briar?
Maybe.
Yours is squishy too?
What else should we
And
do?
and then, okay, now what we're going to do is we're going to see. So we think they're maybe the same thing, hey? Okay, let's take our spoon here, and you're going to first go into this one with a 1 on it. Take a scoop and put it in your cup that has a 1. 1 on your side there. Put it in your cup that has a 1 on it. Put a few scoops in there. Into this one, honey. This one, Briar. Yeah. Okay.
Mommy.
Okay, that's good. Then, you see your water? You can take your water and pour a little bit of the water into your cup.
Why?
Yeah, pour a little bit in here.
More.
More, good job. Okay, now take your spoon and stir it up. You can add some more, honey. You can fill it up about that full. Good job. Okay, then take your spoon and stir it up. Take your spoon and stir it up. Good, good, good. Stir, stir, stir. Okay, now we're going to set that over to the side. Okay, set it over to the side. Because now what we have to do, take our spoon and let's look at the number 2. So take a scoop from the number 2. You can scoop some into your 2 cup. Yep, from here into here. Okay, that's good, that's good. Good job. Okay, now let's add some water. That's good, Caleb. Add some water. Yep, add about the same amount. Good job, buddy. Okay, now take your spoon and stir, stir, stir.
Baby, Mommy.
Is that a baby one?
It kind of looks like we're making soup.
It does, yeah. Now, one of the ways that we can investigate something is by tasting it. So, let's try tasting a little bit of our number 2. See what it tastes like. What does it taste like? Does it taste sweet?
Yes, very sweet.
Very sweet.
Sweeter than honey.
Oh,
So sweet.
I wonder. Okay, now let's take a little taste of our number 1. See what that tastes like.
Yes. Yeah. Yeah, Daddy. That tastes like the ocean water.
Oh, okay. Does it taste very good?
No.
Which one do you think you would want to take another drink of?
This one only. Because
Oh.
that one tastes much better.
Yeah, you can have, sure, go to town there, buddy. Okay, so even though they look the same, they taste different. So do you think that these things might be different things in here?
Yes.
Okay, now there's one more test that
Yes.
there's one more test that we can do.
Yeah.
Yes. Okay, so what we have here is a little light. So I can hold it together like this. Get my thing on the end, and then look what happens when we hold this together. Oh, what happens?
Turns on.
Turns on. Okay, you're not very impressed. Now, let's stick it into our number 2. Now, when it's not connected, does it turn on?
No.
So what you're going to do is you can grab this little thing and dip that wire into the number 2. Let's see, does it turn on?
No.
No. Okay. Now, let's take it and let's dip it into the number 1. What happens?
Turns on.
Turns on. So there's also a difference in whether the light will come on, isn't there? So we learned there are 2 differences between these. Which one tasted sweet? This one. And which one made the light turn on? That one. Now, if something can make the light turn on, that means that it's an electrolyte. Can you say that word?
Electrolyte.
Good job. So this one was salt. And salt is an ionic compound. So it's an electrolyte. It conducts electricity. And this one is sugar, sweeter than honey, just like you said. So it doesn't conduct electricity. It's what we call a non-electrolyte.
A non-electrolyte.
Good job. Thanks for helping, guys. High five.
Let's do that again.
Boom.
Let's do that again.
Okay, so why do these molecules behave differently when they're added to water? Let's look at them one at a time and think about what's happening at the molecular level. So we'll start with sodium chloride. We first have to remember about sodium chloride is that when it exists in the solid state, it exists as a crystal lattice. So we have this alternating 3-dimensional pattern of positive sodium ions that are being attracted to the negative chloride ions by their positive and negative charges. They're ion-ion interactions, which is a relatively strong force. And this would exist in the 3 dimensions, right? There would be this dimension, and this dimension, but we're only going to show 2 here just to make it a little bit simpler and make it a little bit more straightforward. So then we need to take some water. So what we're imagining we're doing is we're taking this sodium chloride and we're going to dump it into a container of water. Now the water molecules, remember that they have an oxygen that's bonded to 2 hydrogens. The oxygen ends up being partially negative, and the 2 hydrogens end up being partially positive. And so this is a polar molecule, and that's going to become pretty important here. That's the reason why oxygen can attract to itself, right? And we can have the intermolecular forces, the hydrogen bonding present between the oxygen molecules. But the oxygen can then also attract to the sodium chloride because of this property as well. And so what the water molecules are going to do is they're going to come in, and as the sodium chloride crystal is added to the water's floating around here, right? There's water everywhere, floating. And as the water molecules encounter the crystal lattice, the negative side of the water molecule is going to be attracted to these positive ions. So the water molecules are going to come in like this, and when they do, they can attract this positive sodium ion and they can pull it into the solution, like so. And so what we'll end up with is a positive sodium ion that's been pulled into the solution, and it gets surrounded by a little pocket of water. Now that's exposed some negative chloride ions over here. And so when water molecules encounter them, they'll line up in the opposite way. The positive side of the water molecule is going to face in towards the ion, and that can enable the water to pull the chloride ion in to the solution as well. And this is going to happen one at a time. The ions will get pulled apart, and each of those ions is going to end up surrounded in its own little pocket of water molecules as they pull the ions into the solution. And so as the sodium chloride dissolves, it also dissociates, and the dissociation is the coming apart of those ions. And it's the dissociation that makes this ionic solution an electrolyte. It can conduct electricity because it has these free ions floating in solution. When I add my solid sugar crystal to water, it also dissolves, as we saw. The glucose molecules, which we've shown here, are made of carbons and oxygens and hydrogens, and they're attracted strongly to each other because they can also hydrogen bond with other glucose molecules. So in the solid glucose crystal, sort of similarly to the crystal lattice. It's not as organized a structure, but the glucose molecules can be attracted to each other like this. Now, when we add the glucose crystal to the water, like we did, the water can also surround the glucose, and it's going to pull it into the solution. The glucose is going to dissolve well in the water because the water can hydrogen bond with these alcohols. These are called hydroxyl groups over here. And they can hydrogen bond with the water, meaning that there's a strong force of attraction between the water and this glucose molecule. And so the glucose molecule can be pulled into the solution and surrounded in a little pocket of water. And then the next one can be pulled off of the crystal. And the next one can be pulled off of the crystal too, right? Each one is surrounded in its own little pocket of water where we're hydrogen bonding between these OHs that are part of the glucose and the OHs that are part of the water. So it is dissolving, just like the salt did, just like the ionic compound did. But the difference here is that it does not get pulled apart into its individual atoms, right? You notice the whole glucose molecule here stayed together. We didn't pull apart these carbons and oxygens and hydrogens. They stay together here. It does not dissociate. And because it does not dissociate, there are no free ions floating around in the solution. These glucoses are neutrally charged. We haven't pulled any ions apart, so this solution is going to be a non-electrolyte. It is not going to conduct electricity. And that's why when we have glucose or any other molecular solution, it is going to be a non-electrolyte. It will not form a conductive solution when it's added to water.
Do that, do that, do that, do